Hello everyone. This is our first video from the image processing or digital image processing series. But I have combined image processing with computer vision and put them all under the same playlist. So this is going to be added to that playlist. So in the computer vision videos, we talked about the models of the camera, perspective projection, camera calibration, and so on. But now at the end of the day, we have to focus on the image and acquiring meaningful higher level abstracts from the images. So what is the image itself? When we look at the digital image, what is it? Well, they are 2D matrices of numbers. Basically, you can look at it as a matrix with a number of rows and a number of columns, right? Let's say 200 rows, 100 columns, something like that. And at each location, at each entry of that matrix, you have a value. What does the value show? The amount of light intensity that the camera CCD has recorded, okay, and digitized, of course, or quantized, because we show it with numbers, really, and we for a regular image, which is of type uint8, this is very common format of the images, uint8, or unsigned integer 8 bits. That's what it is, unsigned integer 8 bits. What are these numbers? Well, these numbers, first of all, they are integers, as it says. They are unsigned, so they are all positive. At most, they can be 0. You won't get the negative number when the image is uint8. And each bit, each pixel value is shown with each pixel value is shown with 8 bits. So we say 8 bits per pixel, right? Or 8 PBPP. There is some S we need here. So 8 bits per pixel or 8 BP. And what range can you record with 8 bits? Each bit is only a 0 or a 1, and if you have 8 bits, then you can record any number from 0 to 2 to the power 8, but minus 1. Why minus 1? Because you already considered 0 as a number. So any number from 0 to 255 is the light intensity that you could have recorded. If you recorded it as 255, means that pixel is the brightest it could, so it appears white. And if it's 0, means you have not recorded any light intensity, so that pixel should appear what? Black, right? So an image can be written as f of r and c. R is the row index, c is the column index. The number is always between 0 to 255 as long as the image is uint8 format. And how many rows do you have? Capital H rows. How many columns do you have? Capital W. So your image is W by H or H by W pixels, right? Okay, and you can see that if, let's say this is this image of this horse, if you look at it like a mesh plot or a surf plot or something, if you look at it in 3D, you see these ups and downs, right? At each pixel, as I said, you have some light intensity. So when it's white, you have peaks. When it's black, you have some deep holes, right? And if you look at it from the top, you definitely see this picture of the horse. But when you rotate it, you're going to see it as a bunch of ups and downs. And if there are areas which are almost the same intensity for that region, you see them as like a plateau, right? So I'm going to show you in a second, but this is basically what it is. And if you zoom into any specific area like here, then you see the pixels, right? Each one of these small squares that you see is a pixel. And each pixel you see has a specific amount of light intensity. By the way, here we are only right now talking about grayscale images. And grayscale means the only type of thing that you see in a pixel is black, white, gray. That's all you can see, shades of gray. You cannot see color right now. I'll tell you in a minute what happens when you have a regular RGB red, green, blue image like this. what's the difference. But right now, just let's assume that the image is a very simple grayscale image, and what would you see, right? So to demonstrate that for you and to show you a relevant MATLAB command here, because I listed all of the MATLAB commands that you need at the end of this lecture, but instead of me going over them at the end, let me use them right now in the context. So here we go. So here I have downloaded an image called spoolbundle.jpg. The first thing I need is to read it into MATLAB. So I say image, I give it a variable name, or image1, whatever you want to call it, is equal to imread. Imread is the command you read an image into MATLAB. And then inside the quotation mark, you provide the name of the file, which is spoolbundle.jpg. If it is in the same folder as you are, all you need is to provide the name of it, dots, the format of it. If it is in a separate folder, then you have to provide the address here behind, right? Like it is in a D drive, like, or E or somewhere else, then you have to provide something like this, correct? So make sure this has the address and the name and format, unless it is in the same folder as you're working, your current directory, basically. Another thing you need to do is make sure you suppress the result with a semicolon. If you don't, what's going to happen? Not only it's going to read it and assign it to image, it is going to show the content of this image. And it's not going to be any nice looking. Look, you're going to get a bunch of numbers, and that is not so nice, right? Look here, if you scroll up, you just see a bunch of numbers, which are basically those numbers I told you about. So make sure when you read an image, you suppress the result, so it doesn't basically type a bunch of numbers on the screen for you. And now, what kind of image is this? If I use the command whose, you see I have one variable image. It is of type uint8, as I told you, and it is 342 by 342 by 3. So it is an image, but it's not a regular image. It's a multi-dimensional image. It's a 3D image, really. It's a 3D matrix. It's a matrix, but it has 342 rows, 342 columns, and 3 dimensions. What are the 3 dimensions? As we're going to see in a second, they are the red, green, and blue components. Okay? And it has these many bytes. Okay? Where did you get those many bytes? Well, remember, you have 342 by 342. So you have what? 116,000 pixels, right? And each pixel, it is going to what? If I multiply this answer by 3 for the moment, you see that's this guy. Why 3? Because you have 3 matrices: red matrix, green matrix, blue matrix. So this number is the same as this, which is the product of all this. It's this many bytes. Is that correct? Yes. Why? Because I told you for each pixel, whether it is in the red, green, blue, or wherever, for each pixel, I need 8 bits, correct? For uint8, 8 bits, and 8 bit is how many bytes? 1 byte. So you see clearly why it is these many bytes. Correct? Good. Now this is clearly not a grayscale image, it's a 3D image. If I want to convert it to a grayscale image, I use RGB to gray. We'll later talk more about conversion of color spaces, but here I will convert image 1 using this built-in function RGB to gray, convert it into a grayscale. Now if you look, this image 1 gray is what? Only 342 by 342. There is no third dimension. So that is a green grayscale image. First, let's look at it. I use the command imshow and pass to it what? The name of the variable. And now you see that's my image. Okay, so this is an image grayscale, as you can see, right? So many rows and so many columns. And if you click on the data tip and click anywhere in the image on any pixel, it shows you the location of the pixel, which is 49 in the X direction, or column 49, row is 15, and the value over there is 111, which is basically, it is, we'll talk about it. What does it mean when it says 111? You can look at 255 for now. It's 255, the maximum number. And why is it maximum? Because you see white, it's the brightest color. And if I click here in the black area, you see the value is only how much? 20, because that's almost completely black. It's not completely, but very close to. So you see the light intensity over there is 20 at the location 96, column 96 and row 281. If I click here also, it's something small, right? 16, 23, 20. Then if I click in the gray area, it's a little bit bigger. If I go in the brighter area, it goes up, it goes up, it goes up. You see, more and more. And when you click in the completely white area, it goes to the max, right? So this is using the data tip. But can I see those 3D plots that I just showed you? Something like this? Sure. Here you need to do a mesh plot, right? So here you have 342 by 342. So this is what you say. You say X and Y is equal to mesh grid of 1 to 342. Okay, and now you get X and Y, and now what you can do, say mesh for me of X and Y and the image 1 gray values. Okay, and here you can see what? You can see those 3D plots I told you. Look at that here. You see, if you see it from the top, you see exactly what you did. But look here. Let me look at it from this direction. See if I can change it here. This is what you see, but now look. If I rotate this, you see, you clearly see a bunch of what? Holes and bridges and canyons and hills, depending on which direction you look at it, right? So here, you see, if you invert it, then you're going to see looking at a bunch of basically hills, but clearly you can see this 3D plot, and if you look at it from another direction, it is definitely the 2D image that you see. You can show a portion of the image if you want with the image show, as long as you use the appropriate number of rows and columns in the matrix. Let's say here I just want to show if I divide it into almost 4 matrices or 4 pieces, I want to show the top left piece, right? So instead of show the whole image, I say what? Show only from row 1 to what? Half of 342 is 171, and the same thing, columns also 1 to 171. Pay attention that the first number you pass to an image is the row index, and the second number you pass to it is the column index. Also, another thing important about images, pixel 1 and 1 is the top left corner. So in an image, the coordinate system is opposite of what you consider. The row starts from 1, goes all the way down, and the column starts from, again, the top left corner and moves to the right as it increases, right? So if I want to show you with arrows here, this is the column, right? Starting from that location and going up, and the row also starts from here and that goes down too. So this is the row, This is the column, and this pixel is 1 and 1, so keep that in mind. So now I say only show me the top left quadrant of this, and now look, you see it only shows that portion of the whole image. If I compare it to the original one, put them side by side, you can see here, right? That I'm only showing this portion of it. Or I can show the image with magnification. So instead of showing the image 1 of figure this one, can come here and add some magnification. So say I am show, then say image 1 gray, right? Then I add some initial magnification, and let me add it as a separate figure so you can see them side by side. And how many percentages? Like, do you want to see the image 10%, 20%? There is even an option called fit, which is like the best fit to the window size, right? But you can provide any number you want. So maybe 50 or so, right? And you can see probably the image at 50% magnification, so you can see them side by side, right? Or as I said, I can do fit. I can make it like several times bigger, like 200 means like twice as big. So the image show gives you the option using this command initial magnification to show the image bigger, and there is another option that you can not only show it magnified, you can also do some interpolation to avoid pixelation of the images. But let's talk about that later when we talk about upsampling and downsampling images. Okay, so we'll keep that for later. Just wanted to show you this option. Now, what is it that makes the quality of a good image, right? How does the quality of an image change with the number of pixels it has and with the number of shades of gray it has? We call them spatial resolution and intensity resolution. Intensity resolution comes from the number of bits per pixel, and spatial resolution comes from the number of rows and the number of columns. What's the effect of those on the quality of your images? So here on the left, you can see 6 images of a flower, and from the top left corner to bottom right corner, you are constantly reducing the amount of pixels in the horizontal and vertical direction. And as you can see, when you get to a low number of pixels, the image is really pixelated, very low quality. So when I say pixelated, that means you can see the visible pixels. You do not see smooth edges and smooth transitions like you see here, going from the dark area to the flower petals. You don't see these clear, nice edges. You see these kind of jagged edges. This is the pixelation, or the effect of a significant downsampling of the image. So you clearly see the more pixels you use to show details of something, of course, you are going to have much better image quality. The other thing is the shades of gray. Here you can see on the top left corner, you have all 256 levels of light intensity. So it's a uint8 going from 0 to 255 or 256 levels. And you're reducing it constantly, 128, 64, 32, 8, and finally 2. When you go to 2 levels, all you have is only white or gray, black, I'm sorry. There is no gray. So this image that you see down here, which is only black and white, right? This guy, this one is called black and white, or another name that you use a lot for it is called binary. So if you hear the word binary image, that's this guy. And although the binary image might look still nice and you still have visible edges, but you definitely are missing a lot of details, right? Look at all these edges that you see here in gray. You don't see any of that in this white area. right? Or let's say all of these small lines of fabric, right? You don't see any of that. Many of the details are going to be gone. And in some other shades of gray, you clearly can see the quantization effects over this region, right? Look here. Because you cannot have a smooth transition of shades of gray. You jump from one level to another level, which is far below or far above it. And so the gradient of the color, the gradient of the gray color that you had, you don't have anymore. So you see all of these blobs appearing out of nowhere. So of course, the better image is always with more shades of gray or bits per pixel and with a higher number of pixels. And I'll show you later when we downsample the image, whether in terms of bit per pixels or the spatial resolution. I'll show you later how we can achieve any of these images, okay? Now, as I told you, in real world, the images that we capture have three layers, three matrices. Red matrix, blue matrix, green matrix, RGB, or red, green, and blue. So in your camera CCD or charge coupled device, you really have filters for gray color, red color, and blue color like this guy. You see, each one of these cells is responsible for one of the colors. Another important thing that you see here is not at every location you have all three lenses. No. In one you have blue, in one you have red, in one you have green, but they are adjacent to each other. So you never have an area where 3-4 adjacent basically micro lenses or micro receivers are all green or all blue or all red. They are distributed in a specific pattern all over the surface of the CCD. More you have green compared to red and blue, and that's why because a big portion of the wavelength of visible light is green, as we'll see later. But there is also here you can see in this 16 arrangement, or it's less than 16 actually, you have 5 reds and 4 blues. And then you have about 12 greenhouses. Okay, so you have basically 21 locations, 12 green, or 16 green, I'm sorry, 16 green, 5 red, and 4 blue, right? So overall 25 cells. So, and these proportions all coming from the amount of green, blue, and red components in visible light that we will be discussing. So your matrix, now your image has 3 matrices, a red matrix, a green matrix, a blue matrix. This is channel 1, this is channel 2, this is channel 3. So if you want to show each one of these channels, how would you do it? Let me show you. So here, I'm going to read the same image that I had. That was basically the spool bundle .jpg. But I'm not going to convert it to grayscale using RGB to gray. I'm just going to show the image as is. Right? Clearly you see the image is colored. Clearly you see here is 342 by 342 by 3. Right? So there are 3 layers. This is the original image. And then I can show next to it what? Let's say the red channel. So I can say what? Figure. And then say I am show image, but not all of the channels, all rows, all columns, but channel 1. Channel 1 means red, and then say what? Title red channel. Correct? So this is the red channel right next to the image. If I show it to you, you might say, what does that mean? To me, that looks like the RGB to gray. It might look like, but I'll tell you the difference. Here, which spools are white? White means what? As we learned, means high intensity. Which spools are red? Clearly, you see the spool that was red in real life. Now it has a big white value. And other colors that have huge amount of red in them, like purple, pink, you see, they have to a good extent. White does. We'll talk about why. Yellow does, and then what? Orange does. But blue doesn't. Blue has minimal overlap with red. So the blue appears black here. Why? Because there is not too much of red in blue. In green, there is a little bit. In black, of course, there is no color. Later, we're going to talk about combination of colors, red, green, and blue, and creating any color that you want. So later, when we talk about color spaces, right, the RGB color space, HSV, and so many other color spaces, we'll talk about with a combination of red, green, and blue, you can make any color that you want. And that's one of the reasons out of all these different colors we have in nature, these sensors are only red, green, and blue, because with these primary colors, you can mix any proportion of them and get what? Any color that you want. For example, if you mix all three colors with the same proportion, add them all together, red, green, and blue, what color would you get? You get white. If you do not add anything, you have black, right? But then, for example, if you mix red and green, right? What color would you get? If you mix red and blue, right? What color would you get? Red and blue, you know, you get a violet, purple, right? Or red and green, what color would you get? That's right. It makes yellow, right? So red and green makes yellow, red and blue makes purple, or you might call it magenta. And then green and blue together makes cyan. Right, so let me just briefly, very fast write it for you. So red plus green, red plus blue, green plus blue, red plus green plus blue, and then none. Right, so none means black. All of them together means white. Green plus blue makes a color called cyan. Red plus blue makes magenta, kind of purplish. And red plus green makes yellow. And with the combination of these four colors, you make a color space called CMYK. Cyan, magenta, yellow, and K for black. And this is the color space that you use in your paper printers. So also with the combination of these four cartridges, if you look inside your printer, you most probably have four cartridges for cyan, magenta, yellow, and black. With these four colors also, you can make any basically object. So we'll talk about color spaces later. I don't want you to dive into the color space conversions, but that's the reason we choose RGB, because with the proper combination of these, we can make any color that you can imagine, right? So, and now I explain to you why is it that the blue has very small red components, because blue and red have minimal overlap in real life, okay? There is almost no blue in the red color, right? But in green, there is a little bit of red, so it's not pure like zero. In red itself, of course, you have a lot. In pink and purple, you have a bunch. In orange, you have some combination, because orange is combination of yellow and red, and yellow itself comes from red and green. So there is a lot of red in orange or in yellow, and so on, right? Now, if I, at the same time, if I look at what the blue channel and the green channel, which parts of this image do you think will turn very white? If I look at the green channel, then this spool should be white because it has the most green in it. And if I look at the blue channel, then this guy that was black in the red channel, now in the blue channel, it will be what? It will be blue. So let me show you that. So here I use a subplot here, as you can see. And now you clearly can see that, hey, this red, in the red, it's a big number. The blue, in the blue area, it's a big number, right? And the green, in the green, is a big number. And then based on the combination, you see different shades of gray. Now you might say, why aren't these images like these? These images that you see, these red, green, and blue, they are overlaid. They are already converted to red, blue, and green. Because when you look at one channel is just a single matrix. It's like a shade of gray. It's like a grayscale image. So these three that you see, they are converted already to three basically channels of images. They took the red channel of that, and then they set the the blue and the green channel of this to 0. So all this guy has is the red channel. Then they combine them back, and this is actually a 3D image itself. If you want, I can make that in a second. So here I did that for you. I wrote a small code. You read the image, you get the sizes. Now if you see, I have 3 new images: the image red, image green, and image blue. For image red, I set the first channel of that, the red channel of that, equal to the red channel of the actual image. But the green channel of that and the blue channel of that, I set them to 0. And since the command zeros of H and W gives me variables of type double, not type uint8, but first channel of image is type uint8, in order to be able to mix them, I do a typecasting here. I convert those double data into uint8. Similarly, I form image green. I set the green channel of that to the green channel of the image, but the red and the blue channel of that to 0. And for the blue channel is equal, the blue channel of image blue is equal to the blue channel of the actual image, but the red and the green channel of that are equal to 0. And then I show them using a subplot. And here we go. You can see the similar pictures to what I showed you here. You can see them right over in this picture, right? So the greenest areas are the parts that have a lot of green, the red areas have a lot of red, and the blue areas have a lot of blue. So any image is a mixture of these 3 channels. Also, since I mentioned several times that red has green in it or green has blue in it, you might say, what are you talking about? Shouldn't these 3 colors be independent from each other? The answer is no, they are not. Okay, they are correlated. Okay, they are not completely independent. Their distributions have overlap. That's why when we want to do advanced image processing and computer vision, we use better color spaces than red, green, and blue. We use like L, A star, B star, or something like that. That is device independent and lighting independent, and so on. So here you can see this is the wavelength in nanometer. This is the visible light spectrum, and these are the intensities of each one of these colors. So you see blue has peaks around like 460, 70 nanometers, and around that wavelength you have a lot of blue in the visible light. Once you go around the I would say 520, 30-ish, that's where you have the peak of green. That is where a lot of visible light is green. And once you go to the like 670, 680 area, that's where you have a lot of red. But at each point, if you look at any wavelength, anywhere from 3 to 800, 900 nanometers, there is always a combination of these 3. So if I come here and say, hey, at 600 nanometer, if the light I'm receiving at 600 nanometer, or it's a range of them, let's say it is between 500 to 600 nanometer range, this is the light that I'm receiving. What color is that? Is that white? Is that blue, red, green? Well, mostly it is white. Why? Because if you look in this range, you have some good mixture of everything. But if you look at any specific point also, let's say even the 600, you have this much of blue, you have this much of red, and this much of green. If you look at 500, you have a lot more blue, some medium green, and very low red, right? And this, let's say 450 again, you have something similar. So these colors do exist in most of the ranges, but below, let's say 480, there is bare minimal green and red, and I would say probably above 650, 700, the red is the dominant. Below 470, 480, the blue is dominant. In the middle, green is dominant. But even still, in let's say range of 6 or 650 or so, green is a big portion. And you can see green covers a lot more from the visible range than blue and red. Green is kind of more dominant. That's why you have here more green receptors than red and blue. Okay, and that's why also you see something that is green, there is what in it? There is also red in it, because it might be here. That green might be here, but if you look, there is also what? There is also red in the green, and there is also blue in the green. So that's why, if you look, if I go back to the picture I showed you, if a spool is green, the red component of that is not zero, it's kind of grayish, not completely black. And the blue component of that also is not pure black, it's close but not pure black, right? Because it's green. But the red wavelength or red color and blue color, they have very minimal overlap. This is the only area I would say that they have a little bit of overlap. If your color is dominant red like this, there is very minimal blue in it, and if it's dominant blue, there is very minimal red in it. That's why you see if the spool is blue, the red, it's the blue component is almost black, and if it's blue, the red component is almost black. So red and blue have minimal overlap. Green is somewhere in the middle, and it spreads most of the wavelength. And there are some more commands that I want to tell you to use in MATLAB, like the command IMWrite, image, sc, image tool, IMProfile, image info, and so on. The command size, I guess I showed you in this code that I wrote. So here, when I pass the image to it, it gives you the number of rows, the number of columns, and the number of channels, which I didn't read, just passed it as tilde. Now, there is the command image info that you can pass if you pass the name of a variable, which involves the data of that image, if you pass it to the image info, do you think it would work, right? Because this command is supposed to give us some information about the image. If I do that, you see, it is not going to work, and that's one of the common mistakes. First of all, this command used to be typed as IMInfo. Now it is changed to image info instead of IMInfo. Okay, so that's one thing. The syntax of the command has changed. The name of the command has changed. Second of all, you don't pass the name of the variable to it. What would you pass to it? The name of the picture. So you have to say what? Spoolbundle.jpg. You pass to it the name of the image, not the variable for the image. And this is supposed to give you what? A window with all of the attributes that it can read. Say, hey, this is a JPEG image. The size of the file is about 18.7 kilobytes. This is the last time that the file is modified. This is where it is. It is true color. It has 3 channels. And this is all it could read. Bit depth is 24. Why? Because you have 8 bits per channel and you have 3 channels. So you have 24 bit depth here. Okay, so that's the command what? IMInfo or image info in the recent versions of MATLAB. If you want to change some image or create some new image and write it as an external image, just like remember in Paint, when you open up an image or let's say Photoshop, you open up an image. you do some modification to it, and now you want to save it as an external image. How would you do that, right? So let's say here, I created image red, right, or image blue or image green. If I say I have this variable image red, correct? Let me show you that one more time. This guy. Can I write it now? Can I save it as some new image? See, because when you save an image in MATLAB, as you know, it is .fig, but you can also save it as what? A .jpeg, a .ping, .tif, or something else. So can I save it as image red? Right? Somewhere in the downloads? Yes. I can do that this way by save as, which you can see here, right? Or I can directly use the command I am right. So I can say I am right, correct? And then here you have to provide what? The variable you want to write, and then the name of the file. So you say this variable image write it as what? Write it as image red.jpg, correct? I write it using a different name. And this one does act very similar to that save as for you, without you needing to show the image first and then save as. Without any of those, just by typing this single command, it does the job of both. And here, you see when I do it, nothing opens, no window, nothing. But if you go here, you see that image is there. And the good thing with this is it does not add the extra boundary to the image. When you save as, one of the things that MATLAB does, unfortunately, it does change the size of the image. Look at this guy. The size of it is 342 by 342, the same size as this guy is, right? But this one, when you save it as JPEG, what does it do? It saves it, but with a lot of white boundary. You see the size is now 562 by 477. So if you want to get the original size back now, you have to do some cropping on this. So if you want to save your images, I would say directly use I am right. Do not use image show and then save as. This is always much preferred. Okay, that's one of the commands, I am show. There is I am tool, there is I am profile. Let me show you those as well. So I am tool, correct? Now, can I pass the variable to this command, I am tool? The answer is yes, you can. What does this do? It gives you a couple of tools for the image. So here it shows you the image, but with a few tools. First of all, as you just move your cursor, hover your cursor or mouse over any pixel, on the bottom left corner of the image, you can see it shows the location and the RGB values. But it gives you a few tools. One of them is cropping, the other one is measuring distance. Let's say you want to know what is the distance from center of the orange spool to the center of blue spool, right? So you click on this ruler, and then you click here at the center of the orange, and then drag to the center of what? Almost blue. And you see it is what? 248.8 pixels. Okay, so it is a very good measuring device for the distances. Okay, that's one of the things you can do. The other thing you can do is see if it allows me to delete this guy. It should. Used to do that. There we go. Is you can crop the image and keep it. So let's say I'm only interested in this portion. You just check that portion and then double click. There we go. It is cropped. Okay, and then you can save it if you want right now. There is also the command I am crop that we will see later, right, when we go to manipulation of images. But it gives you some nice command. As I said, it can also give you magnification, which you have already over there. It can give you image information. It can give you some overview. It doesn't have a ton of tools, but I say it's not too bad. The other command is IMProfile. And you see here that when you pass to it the image, it is not happy, right? It says, what are you talking about? And when it does that, you immediately guess, hey, if it is giving me an error, then most probably it is looking for the name of the image, probably, or it is to be used in a different way than just to pass what? To it the name of the image. So you see here, when you call it, you don't pass to it any image or anything. You just say IMProfile, right? And you can, what does this do? It basically cuts through a line of pixel values on an image and gives you the result in a variable called C. You can even provide how many points do you want. So if you say with n, it samples along that line n pixels and returns to you the profile of those light intensities, either red, green, blue, or all of them. So the command IMProfile does not need the name of the image. Indeed, actually, the image itself has to be first shown. So first you say show the image, then you say what? You say, let's say C is equal to IMProfile. And now it opens the image back again and allows you to draw a line along which you want to sample. So here I go from here to here, maybe double click, and guess what? It showed all of those values, which are 230 by 1 by 3. Why 3? Because it sampled all channels, red, green, and blue. 230 pixels were along that line, and it sampled them. So for example, now I can say plot for me what? C of all rows, column is 1, and then the red channel. Right? And guess what? This is the red samples of the values along that line, right? As you can see, when I go toward the end, and in the beginning I started at orange, ended up at red, the values are high. And then I pass through some areas with low red in them, correct? Or I can look at the blue channel of that line, and so on and so forth. Definitely in the red area I have minimal blue, so my blue values are small. Okay, now I sampled each and every one of the pixels. If I didn't want 230 data, all I could say was IMProfile, let's say just sample 20 pixels along the line, and then it downsampled it from 230 to only 20 values and showed it to me. So that's the command IMProfile. Again, pay attention. The way you use it is C equals IMProfile, and you can even provide what? The number of data points. Okay? The command IMTool, you can pass the variable to it. That's okay. Okay, now what? There is this IMShow with full range or with the range. That command works well when you have a 2D image, a grayscale. So let's say here I say, show me the grayscale version of the image. And it does, like this, right? Now, this is full range. So a pixel can go anywhere from 0 to 255. That's the same as you say something like this. Look. When you say open bracket, means use the maximum range you can and show the image. If I put them side by side, you don't see much of a meaningful difference. Why? Because the image I had was in the range 0 to 255. The minimum was almost 0, the maximum was almost 255, so you don't see much of a stretch of the light intensity. This is basically changing contrast really here. Right, so you see, showing it full scale does not change anything, because the image, if you look at it, if I call this something, as I did in the past, so image gray, if I call it like this, the minimum of image gray was how much? Oh, we'll make sure. Yes, I have to use vectorization. You see, the minimum of it was 0 and the maximum of it was 255. So when I say go full scale like this with open bracket, nothing gonna happen. But if I say what? Instead of full scale, show it only in the range 50 to 100. Then it has to squeeze down the range of 0 to 255 to the range of 50 to 100. Right? So if some pixel is very bright, makes it 100. If it's black, make it 50. So what do you think would happen? Guess what? Here we go. Look at that. You see? Even if it was black, now it is showed with 50 units, so it's not fully black. If it was white, it is showed with white, but if it was not white, it was gray, but still it was above 100. Now it is thresholded down to 100. So you see these two spools for which the light intensities were mostly above 100, now they are also shown as what? The same as white, or these three guys. They are almost shown as entirely white. You see, this is kind of like a truncating or saturation. So the minimum value can be 50, the maximum value can be 100, not 0 and 255. So you can show your image in a what? In a range if you want. And it always typically, if you don't use open brackets, or if the image is open brackets, if you use numbers, you typically bring down the contrast and you ruin the quality of the image. So unless you really know what you're doing, I do not really recommend you do anything like that. This is the image. One other thing I want to show you is the command image sc, which is, although it shows an image, but I do not recommend for regular purposes you replace the command imshow with image sc. For example, if I said imshow image, right, this is what I get. Now, if I say instead figure, and then I say what? Image sc of image, this is what I get. So what's the difference between these two? One thing is definitely, you see the scaling is different, right? The other thing the command image sc does for a regular image, it puts some ticks, x ticks and y ticks for the horizontal and vertical directions. Okay, one thing you can pass to the command image sc is a color map. Okay, that's what it is really. It is using different color maps to show the image. So you see here, it is not showing the image the way it is supposed to. So again, I do not recommend you use the command image sc unless you know the application. But one of the things that it does, if you look at the format of it, is different. You don't pass to it an image variable. What you pass to it is an array C, which involves the full range of colors in a color map. So you have to have a color map where like number 1 corresponds to yellow, number 2 corresponds to blue, number 3 corresponds to something. And then it is going to show those numbers in that color map or show those colors over a range of X and Y as an image. It's not a legitimate original image. So you can see here that here I define a range of colors, and then when I pass this array to the command image sc, it converts those numbers to something similar to an image. It's not really, it's just a pixelated bunch of colors. Okay, and you can add a color bar on the right hand side using the command color bar, or you can specifically tell it which one of these colors goes to which location. So you give it a range of locations 5 to 8 for X, Y 3 to 6, and then say put the color 0 in location, let's say what, 5 and 3. Put the color 2 in location 6 and 3, and so on and so forth, right? So you see it is showing you this kind of color bar map. So it is not really a replacement for the command image show or imshow, although if you pass to it an image variable, it does show some version of that image. One of the good applications of this command is, let's say if you have a mesh plot and you want to show like a contour version of that, or like a projection of different colors on that mesh plot, and color here depends on the height. If you want to project it down below the mesh plot, you can say hold on, and then below the mesh or the surf plot, you pass to it what? The values for the vertical direction, for the z, for the third variable, the function, and say use those and create an image using the values in that c, right? Remember the values in the c, the bigger they are, the lighter the color, or the warmer the color, the smaller they are, the colder the color here, right? Because this is the color map that uses hot and cold for showing the elevation. And then it creates this image down below for you, okay? So again, although this command is there, I do not recommend use image sc for that. There was another command here that I eliminated for this video. Is called axis ij. All this does, it flips the vertical axis from upward downward, and when we get to it for later future plots, I'll tell you exactly how to use axis ij. So I don't want you to be entangled with a ton of built-in commands without knowing how to use them. So hopefully this basic video was useful to you and you learned very basic things how to manipulate images, and I will see you in my next lecture. Thank you.